So I want to discuss about periodic waveforms and the so-called Gibbs phenomenon. So the bottom line is, when you have this is a periodic waveform. In fact, it's a square waveform. Period is 2 pi here. It repeats. This is an odd function because f of t is minus of f of minus t. In any case, a periodic waveform has a Fourier series representation. All these coefficients are real if the waveform is real. And generally cosine and sine terms, omega naught is the period. In this case, period happens to be 2 pi over 2 pi, which is 1. And here, moreover, all the AKs are 0 because it's an odd waveform. So in fact, we can write this representation as simply sigma bk, in this case sine kt, because omega naught is 1, k goes from 1 to infinity. And bk is given by this formula, 1 over 2 over the period integral ft sine kt over the period. Period is minus pi to pi. This is odd, so the product is even. So this integral is 0 to pi 2 times that. But ft is 1 over that region. So integral of sine t is cos kt over k. You substitute the limits, so you get minus 1 to the power k. So what it says is, if it is, when k is even, k is odd, you get 4 over pi k, and k is even, you get 0. So if you want, we can write this as 4 over pi summation sine 2k minus 1 t over 2k minus 1, because of the odd nature. K goes from 1 to infinity. So this expands as sine t plus sine 3t over 3, etc. So it's a slowly converging series. We want to look at the partial behavior of this sum. In other words, what we are interested in is fn of t, which is 4 over pi summation k equal to 1 through n. Not infinity, just a partial sum of sine 2k minus 1 t over 2k minus 1. So by the way, this of course you can represent it as an integral also, because we can write this as 4 over pi summation k equal to 1 through infinity integral 0 to t cos 2k minus 1 x dx, because integral of cos x is sine 2k minus 1 over 2k minus 1. Lower limit 0, upper limit you get this. So if you, in fact, if I, the partial sum also I can write this as 4 over pi integral 0 to t summation k equal to 1 through n cosine of 2k minus 1 x dx. So let me call this sum, and let me show you how to do that summation. So a is going to be cos t plus cos x plus cos 3x, etc. up to cos 2n minus 1x. So best is to write this as the real part of e raised to jx plus e raised to j3x plus etc. e raised to j2n minus 1x. This of course you can write as a real part of e raised to jx. Then you have 1 plus e raised to j2x plus etc. e raised to j2 multiplied by n minus 1x. And this of course sums as 1 minus e raised to, notice that e raised to j2x is the geometric factor, and so this is e raised to j2nx, and here you have e raised to jx, and here we have real part. As we know, we can pull out half of the factor outside, that will cancel with this. Here you get e raised to jx minus e raised to minus jx, that's sine x in the denominator. E raised to jx cancels. Here you pull out e raised to jnx outside. So this will come out to be a real part of sine nx in the numerator divided by sine x. Then you have e raised to j nx. So the real part, this is real, so the real part of this is cosine nx. So you get sine nx multiplied by cos nx divided by sine x. But the numerator is just a sine 2nx. So we have sine 2nx divided by 2 sine x. So I can substitute this here. So if you, and 2 cancel, so if you want, we can also write this as integral 0 to t sine 2nx over sine x dx, this partial sum. So what we want to see is what happens to this partial sum. So the result is that if you compute this partial sum, it will, so this is the original function, this is fn of t, f of t, and the partial sum everywhere else it will hug the function, but except at the points of discontinuity, the function is going to overshoot and undershoot. So this is going to overshoot and this is the overshoot, this is the undershoot. So we want to find out where the overshoot happens and how much is the overshoot. This overshoot is known as the Gibbs phenomenon. And same thing here. So here also you have overshoot, undershoot, and so when you have the jump discontinuity, there is going to be a overshoot. That's what we want to see. So notice that when you have overshoot, you have a maximum, minimum, etc. So we can take the derivative of this function and see, equate it to 0 and see where it is the peaks, etc. Where it goes to 0. So the derivative on the right side is 2 over pi. The derivative of the top limit is 1. Substitute the top limit into the variable. So the equation is sine 2nt over sine t. That's one term. Next term is derivative of the bottom limit, so no contribution. Derivative of this with respect to t. Remember, the derivative is with respect to t. So this is the only term we equate to 0. That gives us the solutions are at pi over 2n. So the first overshoot is actually t1 is going to be at pi over 2n. In fact, if you call it ti, this is going to be multiples of, so the first overshoot is going to be at pi over 2n. So we in fact want to compute this, the partial sum, this one, not the original function, but the partial sum at that point. So we are going to compute the partial sum at t1 equal to pi over 2n and see what happens. So remember, this is of course fn of t. So I substitute t equal to pi over 2n. So this is 2 over pi integral 0 to pi over 2n sine 2nx over sine x dx. So let me call 2nx to be y. So y is 2nx. So when x goes to pi over 2n, you can see the limit goes to 2 over pi integral 0 to pi. Bottom limit is 0, top limit is pi, and this becomes sine y over sine y is now x is y over 2n multiplied by so dx is going to be, you can see dx is going to be dx is dy over 2n. Now here is the final argument. When n as n, we want to study what happens to this function. How do you compute it as n becomes larger and larger? When n becomes larger, y over 2n gets to be close to 0, so that we can approximate sine theta as theta. In that case, this 2n cancels, and essentially this will turn out to be 2 over pi integral 0 to pi sine t over t, which is the standard sinc function, sine t over t dt. I just replaced dy by dt. Now this of course you can numerically expand because sin t is, notice that this is 2 over pi integral sin, this is or sin x over, let's say sin x over x dx. Sin x is x minus x cubed by 3. So this is integral 0 to pi x minus, so x cancels, so 1 minus x squared by 3 factorial plus x 5 also x4 over 5 factorial minus etc dx. So you can integrate a few terms, and then if you substitute the top limit, the answer will turn out to be including this to 2 minus pi squared over 9 plus pi 4 over 300 minus pi 6 over 17 640 etc. So this is going to be if you compute all this is going to be approximately 1.18. That's the whole point. So the moral of the story is this: when you have a jump discontinuity of 2, the overshoot is going to be about here it's going to be about 9%. So the overshoot is about 9%, and 9% here, 9% here. And the interesting thing, as you can see, the final value here, you can already see, is independent of n. So it doesn't matter how many terms we keep adding, this is not going to decrease, this is going to stick around. So what is going to decrease is the first zero is going to, first overshoot is come closer and closer towards the origin 0. But the overshoot amount, because of this peculiarity of the sinc function, is going to stay at 9%. So, of course, we can use a standard technique to reduce the overshoot.